In this example, we're going to find a V0 in the network using Thevenin's theorem. Since this circuit contains both independent current sources and also dependent current sources, it implies that we have to use the general method to solve this problem. So step 1, we're going to find open circuit voltage VOC. So we draw the open circuit over here. And since this is the open circuit, we know that Vx that is equal to 0 because there is no current going through this 1 kilo ohm resistor. And since Vx is equal to 0 and this current depends on Vx that is also equal to 0, we can remove this branch because this branch has no current. You can use the definition by using the voltage V1 minus the nodal voltage V2 if we select this node as a reference node. So VOC that is equal to V1 minus V2, and V1 can be calculated from the upper left corner of the circuit, which has a current of 1 milliamp flowing through, so that is negative 1 milliamp times the resistance of 2 plus 1 plus 1. V2 can be found from the current flow through that branch. So this is 4 milliamp flowing through that branch times the resistance of 1K. So in total that is a negative 8 volts. The second step is to find a short circuit current, ISC. So we draw the circuit again. We are looking for the current IC. So this is also a very standard problem from chapter 3. You can use nodal analysis or you can use a loop analysis. Since we already used nodal analysis from the first part, so we're going to use a loop analysis for this part. We have one current source, which is 1 milliamp current source. It's shared by the two meshes. We can either use general loop method or the super mesh method. So we're going to use the super mesh method. In that way, we're going to define the mesh current like this. This is my I1, this is my I2, and this will be my I3, and this will be my I4. In the first mesh, we have current I1 that is equal to 2Vx divided by 1. I'm going to drop 1000 because I'm using the unit of kilo ohm, volts, and a milliamp. I'm not going to carry the units all the time, but I know that this is the unit set that I'm going to use. The second equation, from the second mesh, I have the current constraint between the second mesh and the third mesh. So that is I2 minus I3 that is equal to the current in between, which is 1 milliamp. So I said I'm not going to carry the units. So that is equal to 1. The third equation that comes from the fourth mesh, I4 that is equal to negative 4 milliamp. The last equation comes from the super mesh that we have. And we know that we can get this super mesh by assuming that we don't have this shared current source that will open up another mesh. And this mesh is called super mesh. This is my super mesh. And I'll write the equation for this super mesh. I have 3K times I2 plus I3 times 1 plus I3 minus I4 times 1 plus I2 minus I1 times 1. That is equal to 0. And since this circuit also contains a dependent current source, so we need to write the last equation, which is a description of the dependent variable Vx. So Vx, that is the voltage here. So Vx that is equal to negative I3 times this 1K. So negative I3 times 1K. Now we have all the equations. So we can solve all these equations for the current. So we find ISC that is equal to current I3 that is equal to negative 1 milliamp. Step 3, which has the form of this, where VTH is equal to VOC, which is equal to negative 8 volts. And the resistance RTH that is equal to VOC divided by ISC, which is negative 8 over negative 1, that is 8 kilo ohm. Step 4, we can start to find V0. We add 1K resistor back into the circuit. So we know that V0 that is equal to 1K over 1K plus 8K times the voltage, which is negative 8. So we find it to be negative 8 over 9 volts.